Good morning. You all are welcome for today's lecture. Last time we have discussed about the Gauss law. So it does demonstrate the net. For example, just assume if you select the surface, something like this, and there might be charge enclosed by this closed surface. Just assume the total charge enclosed by this surface is Q enclosed. So Gaussian theorem states that if you do the surface integration for the flux density, you can represent this one d into ds. Then you can find the total charge enclosed by the selected closed surface. So ds represents the differential surface area of this Gaussian surface. This surface we call the Gaussian surface. So there might be some electric flux across this surface. So total flux go through this closed surface. You can find by using the surface integration of this flux density. As a result, you can find the total charge enclosed by this closed surface. So we will try to do one example based on this Gaussian theorem. Just assume you have a line charge. Just assume this is a line charge with having line charge density of rho L coulomb per meter. So if you want to find the flux density at this point, just assume you want to compute the flux density on this point. So what you have to do, you have to select appropriate Gaussian surface. Here I will refer this type of Gaussian surface, like cylindrical types. So I will select the point what I interest, which is on this surface of this Gaussian surface. So just assume this is a line charge, and if you want to find this flux density due to this line charge. So I will refer this Gaussian surface. This one we call the Gaussian surface. So there might be flux go through this surface, something like this. So if you want to find the flux density, you have to use the Gaussian theorem, something like that. You can represent that one. So if you want to compute the flux density on this point P, just assume this is a point P. So if you want to find the flux density at point P, what you have to do, just apply the Gaussian law. So total charge enclosed by this surface is located here. You can see from here to here represent the total charge enclosed by this Gaussian surface. Just assume the height of this cylinder is simple h, and then total charge enclosed by this Gaussian surface you can represent Q enclosed equal rho L into H. With the support of the Gaussian law, you can write down now the total charge enclosed. You can write down surface. You have to do the surface integration for the selected Gaussian surface d into ds. So Q enclosed equal to rho L into simple h, and d you can select this type of coordinate system. You can select this type of coordinate system. Just assume this is y-axis and this x-axis. And I take this axis and this z-axis. And then you can write down this one. Surface integration of this d into ds equal I'll take this d into outside of s into ds. And as a result, you will get this amount as d into 2 phi r into h. By referring this equation, you can find the equation for d equal rho L divided by 2 phi r into ur. I'll refer here ur is a unit vector along this r. So this is the method how we apply the Gaussian theorem. By doing the surface integration for the flux density, you can compute the net charge enclosed by the selected surface area. You can select any shape of Gaussian surface. For your easiness, better to select the Gaussian surface which is perpendicular to the electric field or electric flux or flux density. So please note down this one. This is one example how to apply this Gauss law to find the electric field density or density vector. Density vector. So I go to new topic. Electrostatic potential. Electrostatic potential. This electrostatic potential we define as the potential at any point is the potential difference between that point and the chosen point at which the potential is zero. I'll explain what it does mean. Just assume there's a point A and point B. So this is the electric field. Electric field intensity is E. Just assume there's an electric field. So when you go through this contour from point A to B, you can go on this way or this way. You can go on this way. I refer this contour path C1. I will mark this contour path along this way to be a closed loop. This is just a loop or a path you are selecting from A to B. So just assume if you move a point charge through this contour C1, just assume you are moving point charge from A to B via the contour C1. And then the work done against this electric field, you can write down dW equal F into dl. So I refer here differential length on this contour path dl. So work done when you move any charge through the differential length of dl, you can write down F into dl. If you can, in addition to that, there's a notation we put here minus. This minus symbol or negative signal indicates that the work is done by an external agent. If you place the positive charge here, there might be some repulsive force. Therefore, the work done by the external agent, therefore we represent this minus notation. So you can write down this one. Force you can compute electric field into the charge. Therefore, if you substitute here minus Q into electric field intensity into dl. You can write down something like this. Therefore, total charge when you move this point charge from point A to point B, work done by this external agent, you can write down W equal minus Q into, have to do the line integration from A to B E into dl. Keep in mind that this negative sign indicates that the work is done by an external agent. This one represents the total work done. This one represents total work done, or potential energy requires in moving, required in moving Q from A to B. Total work done, or you can represent this one, potential energy required to move in this Q from A to B, represented by this equation. Therefore, potential difference we define, therefore, potential difference we define V equal, just divide the total work done when you move from this point Q to A to B, just divide by the charge. This one represents the total work done for the unit charge. Is represent the potential difference between A and B. Therefore, you can write down this V equal W divided by Q equal minus A to B into EdA. So this one represents the potential difference in between A to B. So once you do the line integration for this contour C1, you can find the potential difference in between A and B. This one represents the potential difference in between A and B. A and B. As well as keep in mind that this potential difference of VA equal minus VAB minus VAB. This VBA will represent VB minus VA, or we call the potential at, yes, we refer this one potential at point B with respect to point A. This one we call the potential at point B with respect to point A. Therefore, this VBA we can write down my V minus VAB. So that relationship you have to memorize. So please write down this one. I have to clear this one. So put the heading as the potential or electrostatic potential. So write down the definition, the potential at any point. So write down the definition for this. The potential at any point is the potential difference, between that point and a chosen point within a bracket reference point, or we call the reference point within a bracket reference point at which the potential is zero, In other words, by assuming zero potential at infinity, the potential at distance r from the point charge is the work done per unit charge, by an external agent in transferring a test charge from infinity to that point. Infinity to that point. In other words, by assuming zero potential at infinity, comma, the potential at distance r from the point charge is the work done per unit charge by an external agent in transferring a test charge from infinity to that point. We define as the potential at any point. So please write down. I will show the relationship for this one. Firstly, note down this one. Firstly, note down this one. I will explain this one. This E represents the electric field intensity. C1 and C2 represent the contours or charge moving path represented by this C1 and C2. Please write down. I need to clear the screen to continue the next step. So I'll go to the next step. So I have a relationship for this one. VBA equal minus VAB. Therefore, we can write down VBA plus VAB equals 0. As well as this V, you can compute by doing the line integration of this E into dl. E into dl. Therefore, if you do the line integration for the closed loop, if you do this line integration of the closed loop from C with the C and on the C and C2, as shown in the picture, the path is shown in the picture. You can write down this one. So this results become 0. Once you do the, just assume if you have a electric field or something. So if you select this type of closed loop, C1, and C2. So if you do the line integration for this closed loop, then the final results for this closed loop equals 0. Therefore, I can write down from Stokes theorem, you can check your lecture note, what does this mean? So you can write down this one, line integration of this E into dl equal from Stokes theorem curl E into ds. So if you do this line integration for the closed loop, this result becomes 0. Therefore, to be this one equals 0, this term should be equal 0. Therefore, curl E equals 0. If this E is conservative vector, is a conservative vector, then this curl E should be equal to 0. Keep in mind that. If this E is a conservative vector, then this result becomes 0. This one we call the curl E. Curl E. So we define the potential from the way we define potential. V equal minus E into dl. This is the definition how to compute the potential difference or the potential at point with respect to the point which is selected away from the infinity. So dV, then you can write down minus E into dl, or you can write down this one minus Ex dx minus Ey dy minus Ez dz, you can write down. From the calculus of multivariable total charge, we can, or total potential, we can write down dV equal daba v divided by daba x into dx plus daba v divided by daba y into dy plus daba v divided by daba z into dz. You can write down. Then what you can do by comparing these two equations, by comparing these equations, you can write down Ex equal minus daba v divided by daba x, and Ey component you can write down minus daba v divided by daba y, and Ez you can write down minus daba v divided by daba z. So this relationship you can write down E equal minus gradient v, minus gradient v. By comparing this relationship, you can write down this is represent E equal gradient of V. V is a scalar field. So this gradient of scalar field represent the electric field intensity. So write down this one. This is interesting finding. Gradient of this minus into gradient V represent the electric field intensity. This term represent the gradient V. Gradient. The gradient represent the, can you remember, the rate of change of the scalar field. This gradient represent the rate of the change of the scalar field. So the minus into this gradient V represent the electric field intensity, the given point. By equating these terms, we have derived this relationship. This Ex, Ey, Ez, we compare with this dV divided by dx. By comparing these terms, we have derived this relationship. So I'll go to the next slide. Just assume there's a point charge of Q. I have selected 2 points, A and B, A and B. This one representing point A with respect to this unit charge, and this is the point B. With respect to this point P, I represent the point vector or the position vector as RA, and with respect to this point P, I'll refer this vector as RB. The electric field intensity, just assume this is the contour path. Just assume this is contour path C1, and you can refer here the vector of RA, so variable vector RA, then electric field at this point, E, you can write down E equal Q divided by 4 pi epsilon R squared into UR. UR represents the unit vector along this electric field intensity, or with respect to this R vector. Now, the potential difference in between this VBA, or you can write down this on VB minus VA, you can write down by doing the line integration for the electric field intensity along this contour C. So if you refer this line integration RA to RB, you can write down E into dA. So I will refer here differential length on this path. TL is this differential length. Now, if I substitute for this E with the support of the charge and distance, I write down U divided by 4 pi epsilon R squared into UR dr. Now, once you do this integration, as a result, you will get Q divided by 4 pi epsilon naught into 1 minus RB minus RA by doing this line integration. This VBA may regarded as a potential at point B with reference to capital A. This one we call the potential at B with reference to capital A. So when you move this RA vector to infinity, then VB minus VA almost equal to Q divided by 4 pi epsilon naught into RB. When you move this RA to infinity, then this term becomes 0. Therefore, VB equal, you can write down Q divided by 4 pi epsilon naught into RB. So this is the equation for the electric potential. If you locate the point charge on the point P, due to this point charge, the potential at point B, you can write down something like this. So here we refer this potential with respect to point A. Point A, we assume that is located away from this point B. The chosen point we are selecting at which the potential is 0. So I selected this point A as the potential 0. To bring that one to potential into 0, you have to increase this RA. If your chosen point is located infinity with respect to point B, then this RS goes to infinity. When this RS goes to infinity, this 1 over RA goes to 0. Therefore, we assume the potential at point A, we assume VA equal to almost zero. That's the idea here. So I try to derive the equation for the potential at point B due to point charge of capital Q. So basically, keep in mind that that's the interesting thing here. The potential at any point, we define the potential difference between that point and chosen point at which the potential is zero. Keep in mind that potential is the potential difference. So one point you are selecting with having potential zero. With respect to that point, you are expressing the potential at any point. So here referred point is A, you are expressing the potential for point B due to this point charge of Q. Due to this point charge of Q, it produces some electric field on this space. Therefore, the potential at point B represented by using this equation. To derive this equation, you have to select the 2 points and you have to find the potential difference. With the support of this potential difference, you can express the potential at any point by moving the selected other point to infinity to set its point potential to zero. If this point A is located compared with this point P, with the far away, then potential at point A becomes zero. You are selecting some reference point. With respect to that reference point, with having a zero potential, you are expressing the potential at any point. So the idea is here, we are computing or we are deriving an equation for potential at point B due to this point charge of Q by referring potential difference. The chosen point should have a potential of zero to express the potential at point B. So we will try to do one example. We will try to do simple example. Please write down this one. Please write down this one. Please write down this one, then I'll do one example, get some idea. All lecture videos I will upload to the LMS. So check that videos, I'll upload it. Few videos I have uploaded, so check whether the LMS is visible for you. Check whether the LMS is visible for you. If they ask the enrollment key, just type ABC123. If they ask enrollment key, just type ABC123. Then you can easily go to the LMS. Please check the LMS if it is visible or not. Gunitalaka given feedback, he mentioned that LM is visible for them, then no problem. If it's visible, then no problem. Actually, this method is good because then you don't need the cookies. So if you have a doubt, again, you can see the video, then you can get the idea. This online we can use as positively. There are some drawbacks that is there, but there are some good things. So we'll try to do one example. One example. The given potential, write down the question. The given potential V equal sine theta cos phi. Find the electric flux density, capital D at point simple question. Second part, calculate the work done in moving a 10 microcoulomb charge from point A, coordinates are given 1, 30 degree, 120 degree, to point B, 4, 90 degree, 60 degree. So refer this one. And by referring this one represents the spherical coordinates. Okay, these values are given with respect to the spherical coordinates, not the cylindrical or Cartesian coordinates. They are given r, theta, and phi angles. They have given r, theta, is some theta, r is some theta, and phi. So just try to find the solutions for the given question. To find the solution for the first part, please refer E equal minus gradient V. V is a scalar field. So you can write down this one. Can you remember? Minus da bar V divided by da bar R into UR plus 1 over R da bar V divided by da bar theta into U theta plus R sin theta into da bar V divided by da bar phi into U phi. So refer this expansion. This is the equation for the gradient V with respect to the spherical coordinate system. As a result, you will get that. Check the solutions. 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 So check the solutions. Now just substitute the given point. They have given the point A, the coordinates 2, pi by 2, and 0 degree. So substitute this value, then you can find the value for the flux density. Sorry, yeah, electric field density. I clear the screen. So as you know, flux density or density vector D, you can find permittivity into electric field intensity. Therefore, D you can write down. So you have equation for E. And then you can write down, its coordinates are given, R equal 2, theta equal 5 by 2, and phi equals 0. Once you substitute this given value, you can find the results. This term becomes 0. Therefore, final solution becomes 2.5 permittivity into UR. Coulomb per square meter is the unit. Or if you substitute the permittivity for the free space, the solution is 22.1 UR pico Coulomb per square meter. So this is the way. Firstly, derive the electric field intensity. Then, with the support of this relationship, as you know, flux density vector independent from the permittivity. Therefore, just multiply the electric field intensity by the permittivity to compute the flux density or density vector. To compute the density vector. To do the second part, what you have to do, I give the guideline, you can try. W you can compute minus Q into, have to do line integration between the given points, E into dl. So I have derived the equation for E, then you have to continue. Just check the solutions. These solutions should be 28.125 microjoule. So refer this definition and do the line integration in between the given 2 points. For this one equal to Q into VB minus VA. Both are correct. You can find the value for VB because they given the equation for the potential. They will substitute the points B coordinates to the VB and substitute the given points of A to the potential equation, and then this is the easy method. No need to do the line integration because they have given the equation for the potential. Therefore, just substitute the coordinates of B and A and see the results. This is one method. Or else you can compute the energy by multiplying the potential difference by the charge we are moving. The potential difference you can easily compute because they have given the equation for the potential. So no need to follow this first method. This is the easiest method. Why? They have given the equation for potential. Therefore, just find the potential at point A and point B and compute the difference of the potential and then multiply that potential difference by the charge you have moved from A to B. So that's the idea. So I will stop today's lecture. So we'll meet tomorrow. Have a nice day for